So for this one, we have a long cylindrical steel rod. And so we know the K, and you'll notice this is in imperial units, but it won't make much of a difference for the analysis. So we're given the K, we're given the alpha. Maybe I'll just write down what we're given rather than the value to save time. We know the velocity. We know this is going at 7 feet per minute. We know the heat transfer coefficient in the oven. So we know this H. So some idea of how heat's kind of moving around in there. And we want to determine the center line temperature. So we're interested just in the center line. So if you work through the homework, you'll know that that's a little easier than trying to find it on the edge. And we want to solve it. Anyway, we won't worry about that. Okay, so the idea here is we basically have this rod moving through the oven, and so it's exposed to some initial temperature, and then so the rods enter the oven at 70 degrees Fahrenheit, and so outside we assume that it's kind of a uniform temperature, so that before if we plot the temperature, it's going to be uniform at 70 degrees Fahrenheit, and then afterwards, after, it's going to look something more like this, our temperature profile. And this is the idea behind a lot of this course, is that there's not uniform temperature throughout it. And then so we want to find very specifically this temperature. Okay, so a couple steps here. First thing we'll do is just figure out how long it's in the oven. That we're going to use the speed for. So the temperature, or the time in which it's on within the oven is length of the oven divided by the velocity. This is equal to 21 feet over 7 feet per minute. Which is 3 minutes, which is 180 seconds. The next step is to calculate the BO number. So BO, this is equal to H R naught over K, or rather R. So remembering that this is actually the characteristic length, but we've kind of done it enough for cylinders now that we're used to the fact that it's just R, because all the pi's and everything else cancel out. So weird, a little bit weirder with the units conversions. That's where this 12 comes from, because we're dealing with imperial. And this will give us 0.4307, say. Okay, so a couple of things. First, the BO number is non-dimensional, which is nice. I'm missing a degrees Fahrenheit here, which is nice because it means that these rules that we set up that we're used to dealing with in metric also apply to imperial. So this is just 0.43. It's not feet or meters or anything like that. And so the same rules apply. And usually what we say is if this is greater than 0.1, we have to assume it's non-uniform. And so in your quiz question, you were assuming it's uniform. I don't know if that's giving anything away. I'm sure you figured that much out by now. So assume non-uniform. So now the idea is what kind of equation we need to use in order to solve this. And this actually also depends on another factor. It's the time constant. But the way we do this is, I'll just bring the textbook in here for 1 second. It was in the right place. Right. So the answer to this question is actually these fairly complicated things, and you need to iterate them. So n equals 1, n equals 2, and this helps you narrow in on the correct solution. But we have these simpler versions for if our time constant is greater than 0.2. That means we're able to just essentially do one iteration. It's very quick and easy. And so usually the trick is we assume that it is that. We do this one iteration, and then we check it afterwards, and then we can determine our answer. So that out of the way. Okay. So assuming that it is the simpler one, we'll use table 4.32. And we'll find the factors that we need. This is specifically for a cylinder. Make sure you're looking up the right one. Cylinder. Okay. You guys can see I'm not a good speller. Oh, okay. I misled us a little bit with the way I worded it. So actually, in this case, you can look up tau right away. So we don't need to assume. We'll solve it right away. Alpha t over r squared. Often you're looking for t, and so you can't find tau. But in this case, we can. So in cases where you can't find this right away, you usually assume, and then you calculate it after. In this case, we have it. 0.243. This is good, so one iteration is enough. So then we can calculate our temperature at our center line. So this is temperature at our center line minus temperature. Infinity is the furnace, so we're referring to the air temperature far enough away from the cylinder. So this infinity doesn't refer to time, it refers to location, I guess. Ti, this is the initial temperature, also of the center line, and this is T infinity. So these are both center line temperatures. So we have it at our current time and then at our initial time. This is equal to A1 e to the minus which is our 1.0996. this will be equal to 0.911. And then we were looking for our temperature at our center line, so we're trying to find this. So when we reorganize that, we'll get a T naught. Actually, I can just do this. So we have T naught is equal to T infinity plus 0.911 Ti minus T infinity. And this will be equal to 215 degrees Fahrenheit. And this will be a case where we don't have to convert to Rankine because we're finding this is going to be equal to an increment of degree Celsius or degree Fahrenheit. This will be equal to degree Fahrenheit. So we're going to take some degree Fahrenheit. We're going to add an increment. And so that's fine. But also don't forget, so degrees Fahrenheit is okay. But you can always use Rankine, which is the equivalent of K. So that's the answer. So again, what we were looking for was after it goes to the oven, what is the center line temperature? We did that by first figuring out how long it's in the oven, then what case we're dealing with. Then, based on the case, we found some properties about that specific case. We made sure that we can use this one iteration method, and then we had this fairly simplified equation at the end, but there were a couple steps to get there. And then we found the center line temperature of our cylinder. Okay, I know that was pretty quick, but does anyone have any questions about that?
Do you mind scroll up a little bit?
Yeah. How much?
That's perfect.
That's good. Okay. Okay. Don't forget, you can always email me. We'll post this as a video and picture. For those who still haven't emailed me about the quiz, you have 2 minutes, so do it now. And I'm going to go through after and just email everyone to let them know I received their email. So if you don't hear from me by, I think, 5:30, then let me know. We can sort it out. As long as it's this quick, I think it'll be fine. Okay.
Just one question.
Yeah.
Why do we go to the table for eigenvalue and area?
So you're referring to these?
Yes.
Yeah, so that is, let's see if I can bring up the textbook. So these are just when you're trying to find your center line temperature. I guess that's what you use. I wish I could give you a more detailed explanation. But these are the coefficients used for one-term approximation of transient one-dimensional heat conduction. So this is kind of what we've narrowed it down to. We're looking for the center line. We know that it's not uniform, and we know that our one-term approximation is good enough.
Okay, before this, we calculate BU number. Does that has to do with this?
Yes. Yeah. So, it's 5:05 now, so it's no issue giving away things for the quiz. The BO number is the way we determine what kind of uniform temperature it is. So the BO number is basically it's a ratio of how much convective energy there is on the surfaces versus how much conduction there is. So if there's not a lot of convection compared to the conduction, so basically you're not removing heat that quickly, but heat is able to redistribute really quickly within the solid, then what we call that is a lumped heat capacitance model. We assume temperature is uniform through the whole thing, like through the whole process. So even though, so it starts at uniform at 70, and then it would increase in temperature, all uniform across the body. That's if this was low enough, but because it is higher, we have this situation where it's actually going to be removed from the site faster than it is before it
That makes sense.
redistributes.
Okay. Yeah, perfect. Thank you.
Okay.